welcome. So yeah, so the plan for today is to kind of wrap up what we were in the middle of talking about last time, which was doing some existence proofs and disproof. And then we can just get ready for the exam. So I'll just kind of ask if you've got some questions about the exam, we'll get to them. I just want to kind of first tie up the loose ends that we were in the middle of talking about last time. But so before we get started, any questions that you guys have from the get-go? Okay, so I did upload your comments for the last homework assignment. So I do hope that you guys are kind of downloading those and taking a look at them because I think that's honestly where most of the, not most, but that's where a lot of learning occurs, is kind of getting some feedback on your work and trying to correct it. So definitely takes me, not that I'm complaining, it takes me a lot of time to go through them and give you guys some thoughtful comments so that it's helpful. So I hope that it is. And so just with that in mind, I took out some clips of homework that people are submitting. So this is, I didn't ask for permission, but no one is tagged here. So these are all great assignments. And there's a reason why I kind of want to share some of these things with you, because either a lot of people made sort of a similar mistake, or I think it's kind of a really subtle thing that might be worth pointing out. So here's work from somebody. This was problem 7 on the last homework assignment, where it asked you to prove this using contrapositive. And so one thing that I saw come up with people is this was not an isolated case, and that I used case there, that these are not technically cases. So we use cases for a very special thing within a proof. And so I understand what the person who wrote this or people that did this are saying here, but to make it more clear to a reader, what's actually going on is we're proving 2 directions of this, since this is an if and only if. So we've got statement P over here, we have statement Q over here. And so if I'm looking at this proof, and this is how I kind of check to see what people are doing. If this proof starts by supposing 3n plus 1 is even, right? It's beginning with not P, and then it's getting to the point over here where you have this, and that's not Q. So if we're showing not P implies not Q, this is a part of this proof. Which direction are we proving? Now, is this proving P implies Q, or is this going to prove that Q implies P? That's right. So this is the same as saying this is the contrapositive of Q implies P. So this is actually proving the reverse direction, which is fine. Usually we do the forward direction first, but I suppose you can do them in either order. But because it can be a little bit confusing, right? When we're doing an if and only proof, there's 2 directions. We're doing things by contrapositive. It can get complicated. And so for the sake of yourself and the reader, rather than say like case 1, this would be a reverse direction by contrapositive. And down here, what's actually going on is not a separate case, but this is proving the other direction. So this would be like the forward direction by contrapositive. So these little headings, you can imagine, are extremely helpful for somebody who's trying to read and follow your logic. Any questions just about these labels from the get-go? And just so you know, like when someone sees this thing in blue, you know, what they are going to realize is, well, the reverse direction is this. If this person is doing it by contrapositive, I very clearly know what to expect for the first line and where to go for the last line. Okay, then in this proof, this was probably the most common way that I saw students try and go about this one. And there's an issue here in that when you add two integers, you get an integer. When you subtract two integers, you get an integer. When you multiply two integers, you get an integer. When we divide, we don't know, right? We no longer are going to stay in the world of integers. And so we need to be careful about doing things like this, because now n might not be an integer for certain values of a. Only for very special values of a is that going to be an integer. So when you get to a point like this, you know, and I'm following the logic here. The logic makes sense. You want to show that this is 2 times an integer. The problem is that might not be an integer. So one suggestion for proofs like this, and this happens in both directions, is that if I start with 3n plus 1 is even. And I want to show something about 5n minus 2. Shouldn't use n here. I want to show that this is going to result in something odd. I don't need to solve for n to get there, right? What I need to do is show that 5n minus 2 has a certain form. So why don't I try and do some stuff to the left side to make it look like 5n minus 2. So in other words, I could add 2n to both sides. And we're starting to move closer towards 5n minus 2. And then I could subtract 3 from both sides. And by sticking to the world of adding, subtracting, multiplying things, we're going to be guaranteed that we're going to still just be working with integers. So you want to try and avoid doing some division if possible. And so then at this point, some people stop and they just say like, oh, therefore we see 5n plus 1 is odd. And yeah, I suppose from this, somebody could recognize this form, but that's not the job of the person reading the proof, right? That's the job of the person writing the proof to show that, okay, this has satisfied the definition of what it means to be odd. So from here, you have kind of an intermediate step. We've got this. What else do we want? If we want to get a plus 1 over there, I think we would write it like that. Because that would give us the minus 3. And so now we can see that k plus n minus 3 is an integer because we've assumed all of these things are integers. We know that n is an integer from the initial assumption. We know that k is an integer from the assumption that it's even.
I'm sorry, wouldn't it be -4?
We have
oh, no, wait, never mind, I'm sorry.
Yeah, that's right. It is -4, and then we need to pull that 2 out. Yeah.
I saw it, it just took me a second, sorry.
Yep. No problem. And, you know, to be honest, I learned so much about proofwriting from reading all of your, like, it makes me a better proofwriter reading and correcting and commenting on what you guys are doing. And so I would encourage you to, you know, look at each other's work when you're talking about things and give each other feedback. And don't be afraid to kind of be a little picky about things. That's okay. Yeah. Okay. Any other questions about the work here? So like in spirit, this, I'm not saying this is like, this is a pretty good idea. Like you've got where we need to start, we've got where we need to go, And the kind of gist in the middle had some of the right ideas, but this is not such a subtle thing. So just watch out for that. Okay, here is another proof of the same problem. I just picked off one of the directions. So this student did this one a little bit differently. But here are some nice things. This is really nice. They labeled what direction we're going in. And over here, it just would be nice again to just say, we're going to do this by contrapositive. And then it makes sense that, okay, we're going to start with this thing being odd. That's not Q. Great. And then we're going to try and show that not P is there. So rather than kind of add these little notes over here in the midst of the proof, sometimes it's nice to, you know, you could kind of get this point across by just saying we're doing contrapositive, but that's fine. And so if I'm reading this proof, and I'll put these up online with the solutions in case you're kind of curious about taking a look at these at home. So this is great. Okay, so we know that this is odd. It looks like this. This gives us, okay, we can bring the 2 to the other side by adding it. So that gives us 2a plus 3. Since 2a is even, 3 is odd, thus 5n is odd. And so for something like this, the logic is good here. I just think you need to justify, like, why does that give me 5n being odd, right? And so there's something to connect this and this over here. So try not to leave anything up to the imagination for the reader. So here it could just simply be saying when we add an even number and we add an odd number, that results in an odd number. That's what's going on here. And maybe just say that explicitly. And then we start getting some comments here that these things need to be justified. So because 5n is odd, why does that tell us that n is odd? Right? It's true, it's a true statement, but I think something needs to be said here, namely that, well, if n was even, right, it would look like this, and there's no way that 5 times that could give me something odd. But I do think there should be some justification for something like this, and then a justification for something like this. So I think like each of those sentences are missing something there. So I can see that this is, the logic here is good. It's just missing a couple of details. And so just to kind of let you guys know the level of detail that is appropriate. If you're ever uncertain, do I need to explain that? The answer probably is it can't hurt. And so this was a total different way of doing it, which is actually a really nice way, I think. It doesn't involve kind of, you know, doing algebra. It instead just involves kind of taking a more, you know, a larger view of just what even and odd numbers, properties of even and odd numbers. But any questions about that? So I'm not looking for one way that you guys do them. I'm just looking for ways that are correct, however that might be. Okay, then I want to take a look at question 8. So question 8 was, again, another contrapositive proof, which was, okay, let A and B be integers, and we want to prove if the product is odd, then A and B are odd. Okay, essentially, this is what you need for the previous proof over here, right? That's the comment that's going on here, is that we have 5n is odd. Why does that tell me that n is odd, right? And in fact, you would, if you proved 8 first, then you can say, hey, look at question 8, we proved it over there. But that's why this does need some justification. But so here's the proof, and we're going to do this by contrapositive. And so here's kind of our P, and here's our Q. So the contrapositive would say not A and B are odd. Implies not A, B is odd. And so I do think there's something nice about using the symbolic logic here, and that we have like nice rules about how to negate things rather than try and do them off the top of your head. And so when we negate an and statement, right, saying that both of them are odd, the negation isn't both of them are even, right? It just is one of them has to be even. And that was a really, really common mistake. I would say about half the people had something like this in there, okay, where that should be an or. So here what we should have is, if A or B is not odd, and so instead of saying not odd, right, let's use the definition even. Okay, so that's the contrapositive of the original statement. So that's what we would want to try and show. And so a big thing here, so that was kind of the main problem there. I mean, picking about saying not odd versus even, that's not the biggest deal, but certainly it is nice to make it a little bit cleaner. And so, here's an example of, outside of that and statement, the rest of if we were trying to prove if A and B are not odd, then A, B is not odd, this proof has the right logic, but your proof should be just sentences, complete sentences linking together, making up a paragraph, as opposed to like solving an algebra problem, which some of these do actually wind up coming down to. So I understand that, in previous classes, this was totally fine. We're doing some algebra, and here's how we organize things. Just replace these arrows with what you intend to say. So like things like this, and this, and this, I really don't want to see them in proofs. I would rather see words. Things like equal signs and an element included in a set, those are fine. I'm not saying you need to write out everything in words. But, for example, we would say, suppose A and B are even. That's how I would say that in a sentence. So I'm not, asking for tons of prose, but these should be nice sentences that are kind of strung together. So, I've been trying to give comments on people, and it's been great. I think your proofs are getting coming along much nicer, moving away from the symbols and explaining things. And I've kind of been a little bit lenient, but I think as the exam comes, I don't want to grade your homework one way and then grade your exam a different way. So I kind of graded things on the homework this time, a little bit closer to how they'll be on the exam. And on the exam, you'll get credit if the proof is correct, but you'll lose some points for the style of it if it's not being written out. Any questions about that? And then here's another attempt at this same proof for this one. And let me just say that, so this was a almost totally correct proof. So they have they did this correctly over here. They changed that to an or. And so then this is becoming a case. And so we just want to make sure we label that case 1, and over here is case 2. And I think it's nice to just give a sentence before we jump right into cases, just to motivate where these cases come. So, right, if we're going to prove this thing, we should be starting off with like, okay, let's suppose A or B is even. And when you have things like this or that has to be true, that sometimes is a good opportunity for cases. And so here's one case, A is even. Here's, excuse me, A is even, B is odd. Oh no. Here's another case, A is odd and B is even. Does anyone see an issue with that?
Could you have said something along the lines of without loss of generality and not needed second?
Yeah, so that's one thing we'll think about. That's right. Maybe we could do this without cases. But even if we do it with cases, that's okay. So they've got case 1, A is even, B is odd. Case 2, A is odd and B is even. Does this exhaust all of the possible ways A or B could be even? There's a third case here that hasn't been considered. Yeah, we could have both of them even, that's right. Okay, which is kind of the case that is going on right up here, right? So that it's not like that's a problem. We certainly could do that, but that is a case we would want to consider. So this student did 2 cases. They missed a third case, so this should exhaust everything. So that's one comment. The second comment is we could do this in 2 cases by just saying case 1, A is even, case 2, B is even, and that without claiming anything about the other integer. So in this case over here, we could say A is even, and it's really irrelevant what happens to B. Right? I got AB is equal to 2 times something. That something involves B, and regardless of whether B is even or odd, that thing would still be even. So that's one way you could cut down on needing a third case. And if you look at these proofs, yeah, what Mitchell said was a really good suggestion in that you'll see that case 1, if you do it when A is even, will work exactly the same way if we did a case 2 with B is even. So this is a really good case where you could say, since these cases are going to go exactly the same way, without loss of generality, right? Suppose A is even, right? All that's really saying is without loss of generality, let's assume one of them is even, and it really doesn't matter which one, and then we could just prove it there. So you could avoid cases altogether. If you are going to use cases, that's fine. Just make sure you've considered all of the cases. And if you wind up like getting 8 cases, I would suggest maybe another way of going about it. Any questions? Okay. Yeah, so thanks for those who unwittingly shared your work with the rest of the class. I think it's really helpful. If anybody doesn't want me to share their work after the fact, that's fine. Just let me know about it. But I do think it's useful to kind of see how other people are doing things, and that there's not just one way to do these. Okay, so let's see. Last time we left things right here. That's right. I put some stars here. So we were working with part E. So we were doing existence and disproof type of thing. So the claim here is there exist prime numbers P and Q for which P minus Q equals 97. And kind of we talked about like step 1 in this process is it true or false, right? That might not even be true. So that's what these questions are saying. Decide whether it's true or false, and kind of just some tips, more general tips on the side is if you don't know whether it's true or false, try some basic examples. Okay, you can start picking a whole bunch of prime numbers and it makes sense that one of them would need to be bigger than 97, the other one would need to be less than 97, and see if you can get it to work out. And I would say if you spend more than a couple of minutes trying to find the counterexample and you strike out, then next step might be, well, maybe this is wrong and there is no such pair of numbers. So when we want to prove an existence statement is not correct, when we want to disprove that, what we're going to do is we're going to prove the negation is true. So that's what's going on over here. So then we thought about, well, how can we negate that statement? Sometimes it helps to write things out symbolically since we have rules for how to negate things, right? Remember when we negate an existence statement, we get a for all statement. And then we just negate the conclusion. So the conclusion was there are a pair that equals 97. Now we're going to claim for every pair of prime numbers, there's no way that we are going to get the pair that's going to have a difference of 97. And then another tip is that since we're usually proving conditional things, every for all statement can be rewritten as a conditional statement. And so it might help to reframe that statement as a conditional statement. So this is saying if we have prime numbers, then their difference can't be 97. So that's the logic that we need to get to just to get to the point where, okay, what is the proof that we need to do to answer this question, to show that this statement is false? And I'm going to make a change here. Let's do this by contradiction. Since we haven't talked about any of those proofs. That proof went better on your homework. I didn't make any comments about question 10. That was a contradiction proof. You guys did really well on that one, generally speaking. And so this, these first couple statements help the reader just get in your mentality. Sometimes, you're writing things to yourself almost, and you kind of just assume that the reader is going to be like right there with you. Sometimes I read proofs and they kind of just like pop me right into it. And it's nice to have a header or a couple sentences that just open up to explain, here's going to be my strategy for proving this. And then it helps me kind of see if you're executing that strategy. So we would want to start by supposing the negation of this conditional statement over here. So for when we negate this thing over here, we are going to get an and statement. Okay, so just be aware of that. So we're going to suppose that P and Q are prime. And P minus Q is equal to 97. And what's going on in that stage is that when we negate conditional, we assume the hypothesis is true and the conclusion is false. That's the only way a conditional statement is false. And now we really don't have much of a goal other than to try and get some contradiction out of this. And so far, you know, the only things that we can try and contradict, these are the only claims that we've made so far. So if I can show that P has to be a composite number, Q has to be a composite number, or P minus Q is not 97, then we'd be okay. Okay, so let's go about this in cases. We're going to do case 1. And we're going to think about the different ways that Q could be odd. And the problem with odd numbers, prime numbers, is that you kind of have a special case in that there's one even prime number, which might behave a little bit differently than some of the other prime numbers. So we'll come at it like that. So if Q is equal to 2, and so what can we say next with that?
Therefore is divisible by 3 and is not prime.
Yep. Okay, or various other ways that you could do this. And why is that a good thing to conclude here?
Because it contradicts one of our statements.
Yeah, that's contradiction, right? So that's the goal here, was contradiction. One of the assumptions was that P was prime. And now we just said, well, it's not prime. So both of those things can't be true. So what we can see here is there's no way to do this if Q is 2. But what if Q is some other prime number, which is odd? What do you think would be a good first step for this case?
Let Q equal 3.
So we're going to try and do this in 2 cases. So rather than say like case 1, Q is 2, case 2, Q is 3, case 3, Q is 5, what I'm trying to suggest is that all of those odd cases are going to get proven similarly. So I don't want to pick a special value for Q. This proof is going to work for Q is equal to 3, 5, 7, 11, 13, all of these odd primes.
So do we have to get like the definition of an odd number?
Yeah, let's try that instead. Yeah, so
do you have to clarify it with like the definition of a prime number?
I don't think so. We've assumed that Q is prime.
Oh, okay.
So let's see what happens. Yeah, so go ahead, Giselle. What were you going to say?
Oh, I was just going to say I didn't know that the prime was like implicit or like fully implied for the question. So you don't have to state that it is also prime. You just have to state that Q is equal to 2A plus 1.
Yeah, so we're saying Q is odd and prime. And so each of those things tell us something different, right? The Q being prime means it can only be written as 1 times Q. It can't be broken down other ways. Q being odd tells us this. So this doesn't contradict anything about the definition of being prime. It's just not all odd numbers are prime. But at least this gives us something more concrete than just some like abstract prime number, right? What might be a good next step then?
Don't you want to state 90 P minus Q equals P minus 2K plus 1 equal to 97?
Yep, so then we have P minus 2Q plus 1 is 97. Okay, and again, you know, rather than just write a string of equations, we're just going to kind of narrate our way through this process. So this is going to tell us then that P, if I bring all of these things to the other side, is equal to 2K plus 98. Right, because I would, it's a minus 2, right? I missed that part, yeah. No, what am I saying? We would add the 2K over there. Yeah, sorry.
It should be 96.
And then I'm going to add 1 to the other side as well. So that negative, right, gets distributed to both of those things. So we've got minus 2K. We add 2K to both sides. We have a minus 1 on the left side. So we're going to add plus 1 to both sides. And so how does this get us to a contradiction here?
P is not prime because it's divisible by 2.
Yeah, so we can factor a 2 out. And now this looks like K plus, what do we get here? 46? No. 49, sorry. So that's right, unless K is equal to like minus 48 or something like that, I guess there could be an argument that this could give us back a prime number, which is 2. So this is going to be composite. Okay, as long as that is not equal to 1, right? If that was equal to 1, then we would have a problem here. But here we're dealing with, well, I guess we could say, well, this would mean the only way that would happen is if K was equal to minus 48. In which case Q would be minus 98 So just to kind of make sure you guys are clear with what we're trying to clear up, by assuming it was odd, we're able to get to this, which looks kind of composite, but we just need to be aware that we might have this issue where if that number was 1, then it really would just be saying that P is equal to 2. So what we can see here is that, okay, we do have an issue here, possibly, But if this were the case, then P minus Q would give me 2 minus 97, which is not equal to 97. So if we get the situation where it's possible that this over here is composite, if this thing inside of here is equal to 1, well, that's one case, but that case we don't need to worry about, because if that were the situation, then we get a contradiction with the difference would not be equal to 97. So either way, we reach a contradiction. We just reach two different ones. In one case, we contradict that the difference is equal to 97. In the other case, we contradict that P is prime. Any questions? Okay, so let's see. We've got about 35 minutes to go. You guys want to? I don't know if you want to go through more of these existence disproof examples, or whether you want to just talk more generally about the exam.
I did have one question about one of the PDFs that you put, the mixed practice.
Okay. Yeah, let me just hold off on that for a second. I'm happy to talk about some of those, but I want to just, we're here on this worksheet. So do you guys want to do some more work on these? There are a number that we haven't gotten to, or we can just kind of move on to the mixed practice. I'm getting some other questions. Okay, I'm getting some comments in here. So maybe let's do one more of these. And yeah, let's try a couple more. One of them maybe will be fast. One of them. Yeah, so let's take a look. Sorry, and then I'll definitely do my best to get through some of these other questions. So this one we've done. Okay, let's take a look at C, since this is a power set thing. You guys will have at least some proof that is gonna involve power sets. So definitely be sure you get some practice with those. So again, here the comment is this true or is this false? We don't know if it's true. So what might be, this is always the trickiest part in problems, is like, what do I do first sometimes, right? So who's got a suggestion about what might be a good first thing to start doing if we don't know what to do? We're out of options. Any thoughts? Hopefully you're thinking about it. Yeah, so first thing is, what does it mean to be in a power set? In particular, what does it mean for something to be in this power set would mean, and again, these are sets, right? So this would tell me that X is a subset of A union B. So it might be nice to write out some of these definitions. And if we have another thing, which is in the power set of A, this would tell us that Y is a subset of A. And then we have the last one, which is Z is going to be an element of the power set of B, would imply that Z, maybe I shouldn't use Z since that's integer. This would tell us that W is a subset of B. Yeah, that's definitely helpful to kind of get an idea of what each of these things are, what are elements in these sets. So I don't know whether this is true or false at the moment. Does anyone have an idea of what we might want to do to see which direction we want to move in? So for example, over here we said, let's try some basic examples, right? If we're ever stuck. I would think that initially you might be a little skeptical. I'll just say, because it's a lot easier to give one counter example than it is to prove something in general. So maybe initially you might be looking for the easy way out and say, okay, is there a counter example that I can use? So I think if you don't know what to do, unless you're totally convinced that it's true, I would try some basic examples. You might get lucky and you might see a pattern emerge from trying some basic examples. So it might give you evidence that, you know what, let me stop trying to find counter examples and maybe this is true. Then would give me, what's a really simple set A? So I need to find sets A and B for which this is not true. So if I'm going to try and disprove it,
What about,
so let's see. Yeah, sorry.
What about,
Go ahead, Christina's.
I was going to say, what about trying like the empty set or something really simple?
And what do you want to try for B? Okay, so I see Ken's got some suggestions too. I see your chats coming in, Ken. Is there a question or a comment? Okay. So yeah, let's try this. I think the empty set, first of all, is the simplest set, and it oftentimes can be a counterexample because it's just like it's a different sort of set than the others. So then we can say, okay, if this were the case, what would we get for A union B? If I take the union of the empty set with the set that has the element 1, right? The set A is not going to add any additional elements here. We just get 1. And so now we can take a look at, well, what's the power set of A union B? Right, that would just be these two things over here. Right, it would be all of the subsets of the set containing 1. And then we could try the power set of A. And the only subset of the empty set is the empty set itself. So this is where knowing our definitions with power sets is really important here. For B, its power set would look like that. And so then the union of the power set of A and the power set of B would be, if I take the union of these two things, okay, we get that equality actually worked out in that example. Does anyone see how we can fix this? This statement is not correct. So just be careful. Like, just because it works for one example, you might want to try some more. Any thoughts? So saw that there's a suggestion that came in on the chat. Let's try A to be the set 1, 2, and B to be the set 0, 3. I think before we start adding more elements into these, let's just try it with doing it with sets that have one element in it.
Was the problem there because A was a subset of B?
That's right. Very good point. That's right. We had a kind of a special case there. This empty set actually lived inside of the other set. So let's try like picking two sets which are not subsets of each other, right? But also are not the most complicated thing in the world. So let's just, we started with a really basic example. You say, okay, maybe that one was too special. Let's try something a little more vague, or sorry, a little that has something in it. And so now if we kind of redo this process, let me leave that forward. So if we instead change A to 2, we still try B as 1, and then let's kind of just write out what all of these things would look like. Then we have A union B is that. And so if we write out the power set for A union B, we have the empty set, we have the set 1, we have the set 2, and we have the set 1, 2. Whereas the power set of A would just be the empty set and the set containing 2. And the power set of B is the empty set and the set containing 1. And so now we've got a counter example because this is in this set over here, but it's not going to be in the union of the power set of A and the power set of B.
How come the union of those power sets, they're not, the elements aren't sets themselves?
When we union two power sets, we are going to get things, right? I haven't written out the union of the power sets yet. I just wrote out the power set of A and the power set of B. And so if we take their union down here, then we're going to get empty set. We're going to get the set containing 2. We're going to get the set containing 1, and that's it. So the power set of A union B has this set of 1, 2, whereas the union of the power sets doesn't contain that element 1, 2.
This is besides the point, but I was just wondering if the empty set would be considered intersection between the power set A and the power set B?
Yep, the empty set is going to be an element of every single power set. So you take any two power sets and you look at their intersection, that's the one element that you can be guaranteed is going to be in both of them.
Great, thank you.
Yep. Yeah, I'm sorry. Power sets, Yeah, are a little bit tricky, but I think it's important to kind of get this level of abstraction where we're not just limited to thinking about sets of numbers, because we use sets all over mathematics and we look at sets of sets and sets of other things. So yeah, this gives us an opportunity to kind of broaden our idea of what a set is. Okay, I think I will, I'll put up the solutions to these other ones if you guys want to practice some of these. I'm happy to hang around afterwards as well if you've thought about them and you want to go into any more detail. So I'm just trying to backtrack through the chat here. So I had, I got one request that came in, and I think Mitchell, you had asked for something. If you want to chat in to me what you were thinking, I can try and take a look at that too. So just a couple of general things. Again, you've got kind of the study materials are up online. So if you had a chance to look at those, I did post solutions to that homework 5, which I'm not collecting this morning, so you can check your work against those. But I would just say, when you're thinking about the exam, you know, there are certain things that we've done, like given a statement, find its negation. And I think, you know, rather than get like bogged down in memorizing like every example that we've done this semester, I don't think that's the way you want to prepare for this exam. I think what you want to think about is like, what are some of the general patterns here? And you can think about, well, what are like the different statements and these were basically the different statements that we had. So I think rather than say it like, let me remember how we did this for every single statement, maybe kind of chunk those statements into different categories and then think about, if I want to negate this, then it looks like that. And if I want to negate this, and it looks like that. So having something handy like this to refer to could be helpful during the exam. Like, here is a statement. I need to negate it, right? There's a process here. This is an and statement. Okay, I have a way of negating and statements. So I think it might be nice to have something like this to refer to. And something similar for like, how to give the contrapositive of P implies Q. I think that is looking pretty good for the most part. The problems that I saw in this process were mostly back up here in that there was a breakdown in the negation. So definitely be sure you practice those negations, because yeah, we need them for contrapositive. We need them for proof by contradiction. And okay, know your definitions. What does it mean to be even, odd, composite, prime, in a power set? I'm just listing ones that come to my head. I'm probably forgetting a couple, but I would just go through these worksheets make sure you've got your definitions. I would have them someplace really handy. Don't worry about plagiarizing a definition. Definitions should be really precise. Okay, and then just kind of more generally know your proof techniques. So how do I prove something directly? Usually that's not the issue. How do I do it contrapositive? Contradiction. Okay, I'll add some here. Like in general, how do you prove that a function is injective? We did some of those. How do you prove A is a subset of B? How do you prove A equals B, right? These are types of proofs that we've done a number of them. So I think if you look at these proofs, you'll see kind of some general strategies about kind of how those proofs should follow. So I think it's good to have like a really general sheet of reference that wouldn't be all that long, you know, 1 page. That's general enough so that whatever you see on the exam, you can kind of take this knowledge and adapt it to that situation. So I'll kind of get at these questions that came in. Yeah, so there is something on this worksheet that we haven't talked about that called mixed practice, which one of them says, prove this using a negative method. And so negative method means contrapositive or contradiction, not direct proof. So there's a question about, do we need to know the definition of congruence? Is this in reference to like, you know, like 5 being congruent to 2 mod something or other, that sort of thing?
It is a question on chapter 5.
You know which question?
It's question 19. It's on the book.
Yeah, let me just open that up real quick. What page is it on? You have the page handy?
Let me see.
That's okay. I can kind of scroll through.
It's 319. I mean, the solutions are in page 319.
Where's the question?
Um,
Let me see. I am in chapter 4. Now I'm in chapter 5. Which exercise was it? Which number?
19.
19. Okay, let me share this with you guys. So that's this one over here. Yeah, so this is kind of defined a little bit on that direct proof worksheet, but we didn't get to this yet. So certainly you can read the definitions, and these are good proofs to practice, but I won't ask you about modular arithmetic on the exam. Okay, and I think there was something else, sorry. It'd be much nicer if we were just in this same room and I didn't have to follow this chat. I think there was a question about the homework 5. Question 1A, if I'm catching this correctly. Yeah, okay, let me open that up. so the question was with 1A, and so that R with a positive superscript means positive real, strictly positive real numbers, so greater than 0. And so we've got a map G, which is mapping positive real numbers into the real numbers, and it is defined as this raised to the 4th power map. So let me jot this problem down and then come back to my iPad. Okay, so that's kind of the gist of it there. And so we want to prove or decide whether this is injective or not. And so generally speaking, you know, with a function like this, graphs are a pretty nice way of at least getting like a sense of whether I think this is true or false. So like here's x to the 4th, which is a function, passes the vertical line test. In general, this is not one-to-one because it fails the horizontal line test. But what should we tweak about this graph based on this problem?
Nothing to the left, so it's only going to be positive real numbers.
That's right.
Yes,
Here,
it'll be half of it.
that's right.
Yeah.
So we're kind of starting over here with an open dot, and then it looks like this, since we're restricting ourselves to just the positive numbers. In which case, it does pass this line now, right? So that looks okay. Okay, but this would not be a formal proof of that. So in order to prove this, we have different ways of proving it. And so this is where it might be useful to have like, how do I prove things are injective? And I'm just trying to find the worksheet. That would be like worksheet 9. We defined like 3 ways that you can prove something is injective using direct proof, contrapositive proof, or contradiction. And so the definition is really if x is not equal to y, I'm paraphrasing this very briefly. Okay, which would be, okay, if my inputs are not equal, then their outputs are not going to be equal to each other. So this is the strict definition over here, and this would be like the contrapositive of that. So with these proofs, I would say, you know, oftentimes going about it with contrapositive is a nice way to do these injective proofs because it's a little bit easier to start with things that we know are equal to each other as opposed to starting with things that are not equal to each other. So to kind of just see how that would go, we've got So I'm going to take two things, right, that are in my domain. So they're positive numbers. And let's suppose they give me the same output. And I think when you're doing these, at least some scratch work, to me, it's really helpful to fill in like the first line, where are we starting? And then where are we going? And then let's try and figure out how we can get there. So if we suppose g of x is equal to g of y, this would imply that x to the fourth equals y to the fourth. And then we can take the fourth root of both sides. Right, which doesn't tell us x equals y in general. It would tell us that x could be plus or minus y, because when we take them to the fourth power, right, we're going to get the sign is going to go away. And we would like to show that they're equal to each other. And so this is where we would have a problem. If we were talking about all of the real numbers, this would not be true. We wouldn't be able to claim that this is injective. But since we know that x and y are both positive numbers, they have to have the same sign. Well, and so that would connect us to then x has to equal y. Okay, so we got just a couple minutes left. So I kind of just wanted to make sure it's clear how the exam is going to go. Sorry if you hear a camera. This is me taking attendance. Okay, that's done. And that is, you know, the quiz will be up online just before class starts. So I think it might be a good idea if people could kind of show up a little bit earlier. You're really good at cutting it close, like popping in at like 10:59 and 30 seconds. I would recommend try getting there 5-10 minutes early. Everybody's expected to be on Zoom with their cameras turned on. So try, if possible, find someplace quiet to work. And the quiz, well, it's not a quiz. The first part of the exam is going to look like the quiz is. So it's multiple choice, and you've got 25 minutes to do that. It'll be 10 questions. This is not something that you guys should be able to see, so I won't open it up yet, but you know the instructions are here. And so there are 10 questions. You've got one attempt now for each of those, so be careful about that. And then once you're done with this portion, you can then pop over to work on the written part of the exam. That is going to be over here. And so when you click on this, it'll look similar to like how the homework assignments are laid out. I haven't put the link here yet, but your exam will be a little PDF file over here that you can click on and then just upload your submission in here by 12:15. And if you need some extra time to scan and upload your documents after 12:15, that's okay. But the important thing is that everybody's up on Zoom while you're taking the exam. If you drop out of Zoom, just let me know what's going on. Hopefully that's not a problem. Yeah, so are there any other general questions about the exam?
About how many proofs will there be on the free response?
Yeah, you should expect to prove maybe, 4 things or so of various difficulty, So if I were kind of judging difficulty of things, I would say, like, if this is odd, prove that's even. That would be on the easier spectrum of things, just because we've done so many of those and they have a very specific form. So you'll probably see some of that. And then we've got, up to power sets. And so you should definitely be prepared to see something with power sets as well. So some of them will be easier. You'll have a power set thing. Unless you're told what method to do, you're welcome to choose any method that you want on any of the proofs. Some of them might say, use this method, and then you won't have a choice.
Will there be like, if there's like 4 proofs, are there options? Like, there are 4 that you have to prove, but like, maybe like number 1 has 2 choices and you have to choose one. Or is it just already set? Like, you have to prove this.
You're going to have to prove the questions on the exam. Yeah.
Oh, okay.
I've made the choice.
I was just hoping for like a power set I could get out of it.
Will you put on as to like which proof is worth how much? Obviously the easy ones are not going to be worth as much. If I for some reason get stuck on an easy question and it's only worth 10 points, will I know it's only worth 10 points?
You will have the point totals on the exam, and I grade easy proofs on the same scale as I do difficult ones. So just because I don't know, like if a proof is hard, I feel like it's kind of a jerk to make it like twice as much as an easy proof, right? So in my mind, you've got like, the easy and hard are all relative terms anyway. But in my mind, it's not like I want to penalize you for not being able to do the hardest thing. It's more like if you're unable to do the hardest thing, but you're able to do some of the easier ones, that will balance out the fact that we're only to get halfway through a difficult proof or something like that. But my suggestion to all of you, at least to get some partial credit on anything, would be just write out, like, here's my proof technique. This is what the first sentence would be. This is what the last sentence would be. If you've got those right and you mess up stuff in the middle, you'll still get some credit for that. So we're over time. So you're welcome to go. You're welcome to go anytime, I suppose. But if you want to stick around and you have some questions, I'm happy to stick around as well. Otherwise, Lindsay and I have office hours, so you're welcome to stop by and ask us questions. And otherwise, I'll see you all on Wednesday on exam day.